hurry up. My name is Ausal Barghouthi. I'm going to be chairing this session. I'm from Wisconsin. This session is the better of the two Popple sessions, so you've made the right choice. Slightly better, not much better, just slightly. Our first speaker is Uri, and he's going to tell us about code2vec.
Hi, can you hear me? Hi, everybody. Thank you for joining. I'm excited to see you all here. This is joint work with Mital Zilberstein, Omer Levy, and Eran Yahav. And this talk is about predicting properties of programs using machine learning models. Given a program, we would like to feed it to a trained model and get a prediction of its property. For example, imagine that you're given this piece of Java code that performs some low-level operations on arrays and indices. And instead of carefully reading line by line and trying to understand what it does, we would like a machine learning model to tell us immediately that this code is performing reverse array with a high probability, which is in fact what this code does, or reverse with a lower probability. To perform such predictions, we need to train the model on pairs of programs and their properties, and hope that at test time, when the model observes a program that it has never seen before, it will be able to generalize and predict a likely property. And the best way that we know to do that is using neural networks, which are trained on millions of programs and their properties. And this network is called code2vec. It's a neural network for predicting properties of code. We released it to archive a few months ago and got great positive response. And in the paper, we applied this network for the difficult task of predicting method names. So the program, in our case, was a Java method in which we deleted the method name. And we trained the neural network to predict the method name given its body. However, it's a general approach that has many possible applications, like predicting yes or no a piece of code contains malware, predicting the required dependencies, predicting keywords, hashtags, and clone detection. So how does code2vec work? Let's first talk about what are neural networks, and forget about everything you've been told about how neural networks are imitations of the human brain. I think of neural networks simply as sequences of simple algebraic functions over vectors and matrices. For example, let's take a look at a simpler network that predicts how positive is a given sentence in natural language. So on the left, we have a sentence in natural language, a good talk, and we would like to assign it with a scalar score that represents how positive or negative it is. So one possible way to do that is to start with word vectors, a vector for every word that we observed in our training data. These vectors can either come from an external model, such as code2vec, or what many people don't know is that these vectors can be initialized randomly and just learned with the rest of the network. We then perform a sequence of algebraic transformations. For example, we can average these vectors, and then we can multiply the result by a learned matrix W, and then we can sum the vector's element and get a scalar score. Now, if in addition we have the true score, given by an oracle or somebody had labeled it for us manually, we can compute a loss function between the predicted score and the true score, and then backpropagate this loss back to every learned parameter in the network. And the learned parameters here are the word vectors and the matrix W. And it means that we derive the loss with respect to every learned parameter, and then we update the parameter value by a small step alpha towards the negative gradient. And this process is known as gradient descent. And if we repeat it enough times, the predicted score will get closer and closer to the true score. And hopefully, after observing enough data, the network will be able to assign a likely score for sentences that it has never seen before. So back to our problem, the two main challenges in encoding programs are, first, how to decompose a program into smaller building blocks. And we're looking for a decomposition of building blocks that are small enough to repeat across programs, but on the other hand, large enough to be meaningful. And this is known in the machine learning literature as the bias-variance trade-off. And the second challenge is how to aggregate a set of these building blocks to get a single prediction. So in high level, we take a program, we decompose it to a set of meaningful pieces, we represent each piece as a vector, and we aggregate all vectors to a single code vector in which we use to make the prediction. So for the first challenge of decomposing programs, there is a trade-off between the learning effort that is put on the learning model and the analysis effort. On the one hand, if we use if we learn from the surface text, from the token stream of the program, we put a lot of effort on the learning model because it needs to waste capacity by implicitly relearning from scratch syntactic and semantic regularities. If we use handcrafted features, data flow analysis, or control flow analysis, these are all great, but the more our model relies on them, the more task-specific and language-specific our model becomes. We recently found that using AST Paths is a sweet spot between these two approaches because they take away a lot of the effort from the learning model by leveraging the syntax, but because they are purely syntactic, they don't require us to hard code our knowledge of the semantics of the language into the learning model. So this way, the same algorithm, the same approach, works for many programming languages and many tasks. So what are these AST paths? For example, take a look at this piece of code. It loops while not done, and if some condition is met, done is assigned with true. And we as humans understand that at this point, the loop breaks. To represent this piece of code as AST paths, we parse it to get its abstract syntax tree, its AST, and then we extract paths between leaves in the AST. So for example, let's take a look at one of those paths between these two occurrences of done, which are these two occurrences of done in the AST, and let's see what this path tells us, why it's even meaningful to do that. So this path tells us that done is a symbol reference, which is under negation, which is the condition of a while loop. Inside the while loop, there's an if condition, and if the if is met, there's an assignment in which done is assigned with a new value. So as you can see, this single path tells us much of what's happening in this piece of code. It tells us that done is both a symbol reference under negation, which is the condition of a while loop, and that it is assigned with a new value if an if condition is met inside the while body. And to represent the entire piece of code, we take the set of all the AST paths, so not only the single path, but the set of all the paths between leaves, so also the path between done and true and done in some condition. And we need to represent them as vector. So we use two sets of learned vectors, a set of token vectors and a set of path vectors. Then given a path and the two tokens that it connects, which are the same done and done in this case, but they are usually different from each other. We look up for the tokens from the set of token vectors. We look up for the path from the set of path vectors. We concatenate these three vectors and get a single vector. We multiply it by a learned matrix W that combines them. And we apply an element-wise nonlinearity, such as the hyperbolic tangent function, that rescales every vector element to the interval of -1 and 1. And this is called a fully connected layer. And we get a single vector that we call a path context vector that somehow captures all the information that exists in this path and the two tokens that it connects. Now, this leads us to the second challenge, because this is the vector representation of a single path. But remember that in a piece of code, in an entire snippet, we have many paths. So we need to somehow aggregate a set of these path context vectors into a single code vector. So this brings us to the second challenge. And our input here is a set of vectors representing AST paths. And this set can be of an arbitrary size. And we need to somehow aggregate them to a single code vector. You can think of it intuitively as having many pieces of information that you need to somehow aggregate to make a single conclusion. So one possible approach is to somehow select the most important vector. But as you can imagine, this way we lose the rest of the information. Another approach is maybe to use all vectors by averaging them. But the problem here is that we give an equal weight to some very informative and unique and important vector and some other very common and non-informative vector. And finally, the approach that we found to perform the best is to use attention, which means that we compute a weighted average of these vectors such that the weights in the weighted average are learned and computed by the network. So this is equivalent to taking all pieces of information into account, but focusing more, giving more attention to the important pieces of information. So the idea in attention is that the values of the vectors learn two distinct goals: the semantic meaning of the path context vector, of the path context, and the amount of attention, the amount of focus that this path context should get. So our input is a set of path context vectors, and we have an additional learned attention vector in the neural network, which is also initialized randomly and updated and trained with the rest of the network. Now, to compute the weights in the weighted average, we perform a dot product between every path context vector and the attention vector, and we get scalar scores for each path context vector. We then normalize these scores using a function called softmax, which makes sure that these scores sum to 1. We then multiply each path context vector by its normalized score. And finally, we sum these weighted vectors and get a single code vector. So as you can see, this code vector is a weighted average of the input path context vectors, such that the weights of the weighted average are computed by the network and learned and updated all the time during the training phase. So this brings us to the entire code2vec architecture. We begin with a program. We decompose it to paths to syntactic paths and the 2 tokens that each path connects. We then represent each path and its 2 tokens as vectors, pass them through a fully connected layer that combines each path with its own tokens. And this gives us these orange boxes, which are the path context vectors. We then compute the attention weights and use them to compute the weighted average, which is the code vector. And finally, the last part that I haven't talked about it yet is that we need to train the neural network to do something. We need to have some sort of objective function that the network will try to optimize. So there are many possible things to do here, depending on the task that we're trying to solve. Because we trained the network to predict method names, we used an additional set of method name vectors for every possible method name that we observed in the training data. And we used the code vector to predict the target method name. So when training the network to predict method names, we trained it on 14 million examples. Training time is less than 1 day, which is considered very fast in neural networks. And this is thanks to the simplicity of the network, which allows it to scale to such huge data sets. And I just want to emphasize that the entire network is trained end-to-end. All the learned parameters here, which are the path vectors, the token vectors, the fully connected layer, the attention vector, and the target method name vectors, are all trained and updated simultaneously during the training phase. So here are 2 examples for predictions that were made by the trained network. These are 2 Java methods that are very similar to each other syntactically and textually. But the trained network has managed to capture the subtle differences between them and predict that the left one should be named contains, which is in fact what it does, and the right one should be named get property or get value. The colorful paths that you see on the code are the top attended paths, the top paths that were given the highest attention during the prediction that the network has made. And let's see these paths on the AST, because that's where they really came from. So this is the contains example again. And the widths of the paths here are proportional to the attention scores that the network has given them during the prediction. So for example, the red path from elements through the for each node, through the if statement node, and all the way to return true was given the highest attention. But the prediction was also supported by other paths, such as the blue path from the parameter target and all the way to return false. So as you can see, using attention provides interpretability because we can interpret which paths the network had focused on while making the prediction. Additionally, as a side effect of this entire process, if we take a look at the high-dimensional space of learned method name vectors, it turns out that cosine similar vectors are learned for semantically similar labels. So this is the dimensionality reduction of the high-dimensional space of learned method name vectors. And if we zoom in, we can see that get account, get accounts, and get account number were assigned by the network very similar vectors. So we can take a method name, such as count, and look for the vectors that are mostly similar to the vector of count. And we get count and size, which are indeed very similar semantically to count in Java programs. Additionally, we can take 2 names, equals plus to lower, sum their vectors, and look for the vector that is mostly similar to their sum, and we get equals ignore case, which is indeed almost equivalent to lower casing and then checking for equality. And finally, it turns out that the network has also learned to capture analogies. So it turns out that receive is to download, as send is to, can you guess? Upload, that's right. And the network has learned that by itself. All these analogies and similarities are available in our website at code2vec.org. You can play with them online, or you can download them and use them in other models and other applications. In the website, you can also enter your own piece of code in Java, or take one of our examples and get the prediction and the AST with the top attended paths. And all our code and trained models are available online and are already widely used. So to summarize, the two core ideas in learning code snippets are first representing a code snippet as a set of syntactic paths, and aggregate all paths using neural attention. These two principles lead to a simple and fast-to-train architecture that is also interpretable thanks to the attention mechanism. And finally, the learned vectors capture interesting phenomena. You're welcome again to visit the code2vec.org website, and I'd love to take questions. Thank you.
Thank you. If you have any questions, please come to the front. There's a lot of questions. It went viral. But let me summarize a number of them that have to do with the analogy to word2vec. So in word2vec, you learn the vectors, a vector for each word, independent of the final task that you wanna achieve. So you can learn a bunch of vectors and use it for translation, use it for understanding, and so on. But in your case, you're doing joint training, so the vectors you're learning are tied to the name prediction task. So do these vectors translate to other tasks? And what if you want to make them more general?
Yeah, great question. So even in word2vec, there is a task that word2vec is trying to optimize, which is predicting the center word given its surrounding window of words, or the opposite. Here we also have the objective that the network was trained to predict, which is the target method name vector. I do believe, we haven't tried that yet, it's part of ongoing research, but I do believe that the final vectors can be used for other applications, and these analogies and similarities are an evidence for that. One possible thing that that comes into my mind is that there are domains in which you don't have a lot of data. For example, predicting whether or not a piece of code contains malware. So how many pieces of code that contain malware can you find? Maybe 100, 1,000. So one possible application that they can think of is training our neural network for the task of predicting method names, and then take the trained vectors and transfer them to another task. But it's a great question that we don't yet have a concrete answer.
In all your examples of statement lists, you only had singletons. Each block node only
Sorry, I have what?
You only had singleton statement lists. You had a block which had one successor.
Okay.
So when you have a list of statements, how do you represent the ith element in your path? Is it just one of many, or do you actually say it's the 17th element of this list?
We just take all the pairwise paths between leaves in the AST, regardless of the structure.
Right, but along the path, as you go down, you hit a block, and you have to go into the 17th element of a statement list. Do you record that it is the 17th one?
Yes, we added, just a technical detail, so I didn't mention it. We add a child ID. In the paper, we elaborate on that. We added the child ID to signal which child did we pass from when going from the parent node to the child node. It's especially important, it's less important in the 17th child, but it's mostly important in assignments when you want to know who is assigned and what is the value that you assign, or which is the object and which is the field. So we added that child ID.
Right, so I understand that in assignments you want to know whether it's the first child or the second child. But in a statement list, I would think you'd want less information.
Right, so we also capped this value to up to 3, if I remember correctly. So if it's 17th or 18th, we represented it the same.
Can you imagine to apply this also for names of classes?
It's definitely possible. We didn't try it yet, but based on past research, I think it's definitely possible.
So I was wondering if you could go beyond names and actually do something similar to, produce some understanding of what the code is actually doing. Like I would love for a neural network to, read in a bunch of code and tell me that this code is, traversing data structure and trying to compute, let's say, the maximum element in the data structure. So I would like that sort of output rather than just a name.
Yeah,
Do you think that's feasible?
I definitely think that is feasible. It's just more difficult to evaluate. We used the task of method name prediction as a proxy for a variety of other applications because it is both easy to evaluate and it's very difficult because the set of method names in our model was of size 300,000. So classifying a piece of code to one of 300,000 possible names, I believe that it's a good proxy for other tasks. Specifically predicting about traversing a tree, it's more difficult to evaluate just because we don't have such large data sets of such code, but I definitely think it's possible.
Yeah, okay, thanks.
Let's thank the speaker again.